So, hello everyone. Welcome to our second professional enhancement seminar of this academic year. It's an absolute pleasure to have today with us Dr. Niklas Karlsson of Verizon Media. Niklas has had a long and distinguished career. And he's a pioneer in the area of online advertising, where he's combining tools from feedback control, artificial intelligence, and big data analytics in order to come up with innovative online advertising strategies. Niklas is Chief Scientist and Vice President of Research and Development for Verizon's media demand side platform, and he received his master's degree in engineering physics from Lund University in Sweden, and then another master's degree in statistics and applied probability from University of California at Santa Barbara, and doctoral degree at the same institution in mechanical engineering, but with emphasis on control theory, dynamical systems, and robotics. And he also graduated from the Stanford Executive Program 3 years ago in 2017. So before transitioning to the world of online advertising, Niklas actually was in the area of robotics. So he started his career at Evolution Robotics in Pasadena back in 2002. And when he was with Evolution Robotics, he invented, among other things, their V-Slam technology, which is nowadays used in among other things, in Roomba, autonomous vacuum cleaner, and some of you may know that Evolution Robotics was acquired by iRobot, many years ago. And since 2005, he's been actually in the world of online advertising, first with advertising.com, and later on advertising.com was actually acquired by some other company that eventually became part of Verizon Media. And Niklas holds a number of patents. He has 36 issued patents under his belt, both in the area of mobile autonomous robotics and online advertising. And he's been very active contributor in terms of educational activities as well. He's a senior member of IEEE, and he received a Distinguished Alumni Award from University of California in Santa Barbara in 2015, and the Master Inventor Award from Verizon Media in 2017. And today he's going to tell us about the use of optimization control and machine learning in the area of online advertising. So Niklas, the floor.
Thank you so much, Mihailo. It's a pleasure to be here. Hope some of you are still awake. So I'm happy to be here, and I will tell you then about how we are using some of the techniques that you all are familiar with in the area of online advertising. And the agenda is that I will first give an introduction to the industry to make you appreciate the significance of solving the problems that we deal with. I will demonstrate how we are formulating well-defined optimization problems from the business needs, and describe how we are solving that in a scalable way by leveraging techniques from control, estimation, and big data, etc. We're doing that by leveraging a decoupled solution involving 3 components: event rate estimation, control, and bid shading. And I will wrap up with some concluding remarks. So first, in terms of the industry size, so it's a very big industry, and you can see here some statistics, and the black bars indicate the worldwide digital ad spending. So it is, well over $300 billion per year spent, and more than 50% of that is so-called digital ad spending. So it's advertisement shown online and in video, etc. And it's a rapid growth most years. In the past many years, and over the next few years is expected to be double-digit. And in terms of one specific aspect of digital advertising, so-called programmatic advertising. Programmatic advertising is automated advertising. That's when you are figuring out when and where how to show ads using a robot, essentially. So automatically by human not in the loop, We are collecting data and then trying out to see what type of users will respond favorable on an ad. So this aspect of digital advertising is making up the majority of all the digital ad spending. You can see some of the percentages, and it's so in the area of 70, 80, and expected to grow even further percent of all of the digital ad spending that is called programmatic ad spending. So hopefully those charts speak for themselves in terms of the business significance of online advertising. So the money is there. So then in terms of who are the dominant players? And we can see here in terms of ad revenues, companies that as part of their business model relies on online advertising. There are some of the very well-known companies: Google, Facebook, Alibaba, Amazon, Baidu. A lot of what they are making money on is actually from digital advertising. So just one interesting observation here is that all of the significant companies are either from the US or from China, and it's a pretty small number of companies that are dominating the industry. So all of those companies are, as a result, hiring a lot of people that are able and have the skill set to work on the problems I will describe in this presentation. I will now, before I go into the meat of the presentation, I will just give you sort of an idea about the history and a timeline of online advertising, and I'm presenting it in the context of our company because it turns out that we were one of the first players in the industry. So it was a company that was back then named TechnoServe, which was founded in 1998. It was soon thereafter renamed to advertising.com. They came up with this idea that we could use a machine to figure out when, where, and how to show advertising. And back in '98, it was early in the internet era. And so it wasn't as much data, it wasn't user level data, it was a very coarse segmentation of the data was available. The optimization back then in the early version was just done in the equivalence of an Excel spreadsheet. Soon thereafter, they implemented a solution based on a linear program. And this was the optimization engine of choice for the first 5, 6, 7 years or so. But the industry, both the industry and the company grew. So advertising.com was one of the biggest and most significant players at the time, and had a significant market share. And as the business grew, it became obvious pretty early on that limitations of the linear program solution would not allow the company to continue to grow. So that's when they understood that they needed to incorporate aspects of feedback control. And that's when they start to reach out to try to find someone to help with that paradigm shift. And I joined in 2005, and I was tasked with this undertaking to figure out how to solve the problem in a more scalable manner. So the first scalable and decentralized and feedback-based solution to the optimization system was deployed in 2006. And from then on, we have iterated, we have enhanced the solution, and over those last 15 or so years, more granular data has been made available. So you can see some of the items along this time axis. You see in 2009, we had the first version of user level optimization. That is when we first started making, taking advantage of some information we know about individual users. The platform business sort of changed shape and form, and features were added along the way. And in 2015, the company was acquired by Verizon. So the company at that time was AOL, because AOL had acquired advertising.com back in 2004. And AOL was acquired by Verizon in 2015. Yahoo was acquired by Verizon in 2017. And when that acquisition was finalized, a new entity and subdivision of Verizon was formed, which is now called Verizon Media, and that's the company that I work for. So we're fully owned by Verizon Communications, and we are dealing with online advertising. So that's sort of a time axis, and I could say much more interesting stories around this, but in the interest of time, I will sort of now go over, switch gear to talk about more of the technology and see kind of how things that you have learned actually fit into the solution of this. But to do that, it's useful to understand kind of how ads are being shown online. So assume that you are the guy sitting there on the left on the slide. You are surfing internet and you go to your favorite web page. It might be to watch the latest sports news or any news or anything, Facebook, etc. So when you're entering the URL and load that web page, the publisher content server will present the requested content, which could be an article, a video, some image gallery, etc. But many publishers, they make money on traffic by selling real estate on their web page for advertisement. And that's how the publisher ad server comes into picture. Because what that one is doing, it is taking whatever information that you have agreed to be shareable. It could be nothing at all if you have very tight security settings, or it could be something about, I mean, what type of device you are using. It could be where you are located. It could be about your demographic, etc. So whatever information is shareable will be sent over to so-called supply-side platform that will put up for sale that little real estate on your web page that will, within a few milliseconds, be populated by an ad. But before it's being populated by an ad, that real estate is sold on an open exchange. It's sort of like Wall Street, the stock market. The supply-side platform will announce to all of the potential buyers to say, hey, who wants to show this ad, or who wants to show an ad to Mihailo? And then there's some information about Mihailo that he has agreed to share. And then in real time, then all of the bidders, which are then representing various advertisers, they are making an assessment about how much they think it is worth to them to show an ad to Mihailo. They are submitting a bid. And all those bids are consumed by an auction. They conduct an auction. The highest bidder will win the opportunity to show an ad to Mihailo. And that ad to Mihailo is shown here to you in front of the computer. But then the bidder, the ones showing an ad, they will have to pay for this opportunity. And there are two different cost models used in the industry. It is either a so-called first price cost model or a second price. If an ad is sold based on the first price cost model, then the highest bidder not only then wins the opportunity to show the ad, but they will also pay the same amount that they were submitting as a bid. If it is a so-called second price cost, that means that the highest bidder will pay the price of what the second highest bidder submitted. And all of this happens within just a few milliseconds. So then you can just imagine that some of the constraints that are imposed on the optimization system, because not only does it demand a very, very short latency, we're also talking about billions and billions of impressions being sold every day. And then to that very overarching problem that we'll consider here is the problem from the bidder's point of view, to figure out how much should you bid. So as an advertiser, or if you represent the advertiser, you want to submit the right bid to maximize or some objective function, but there may also be some constraints imposed to it. And there might be a very large number of advertisers. I mean, we talk about thousands, 10,000s of different advertisers that may be interested to submit bids. And each advertiser will submit the bid without cooperating with other bidders. So we are dealing with a non-cooperative game. So and wish to devise a non-cooperative bidding strategy so that the objective of this individual advertiser is met. And we're doing that for an extremely large number of impressions that are being traded every day. So, given this overarching problem, then in order to make use of what we have learned in school, we have to first define a problem. It needs to be well defined. And a very common problem is that we want to maximize the total number of sales, or we can say total number of conversion counts. But we have constraints. We have a budget. So an advertiser may come to us and they may say that we have this $100,000 to spend, and we want to spend it over the course of 1 month. But we don't want to spend all of that the first day or the last day, but we want to spend that smoothly throughout the month. We are also often imposing some constraint on the effective cost per conversion. So although we are paying per impression, but there will, since a small fraction of the impressions will turn into sales, then we can compute what is the effective cost that me as an advertiser will pay per conversion. And we may then impose a constraint on that to say that we want to pay at most, say, $5 effectively per conversion by way of paying per impression. So we're having two constraints. We have a budget constraint and we have constraint on the effective cost per conversion. But besides those constraints, we want to maximize the total number of conversions or sales. And just for future reference, that the definition of ECPA, which stands then for effective cost per conversion, is the total cost paid for the impressions divided by the total conversion count. So this is a pretty clean and pretty standard problem. And in principle, it can be solved with a textbook, so linear program solver. However, it's an extremely high dimension problem, and because we have an extremely high number of possible users that we want to show the ad to, an extremely large number of different user features and etc. So that we can't just throw the textbook solution to it. We need to be smarter than that. So then, to be clear, that why the classical solution doesn't work these days is that it doesn't scale sufficiently. It cannot make full use of the artillery of artificial intelligence and machine learning and all of the available data. It also doesn't automatically learn from its mistakes. So we are missing the opportunity to directly leverage on feedback to say that, well, if we are bidding too much, or there are some type of users that is not performing well, that we are not interested in those, that many of the classical solutions don't actually have kind of a straightforward way to correct for that. And it doesn't sufficiently well adapt to changing competitive landscape. And as a result, it does require frequent human intervention. But the solution we have that needs to be implemented and needs to operate for tens of thousands of different advertisers. We cannot afford to appoint a human individual sitting and holding the hand of the campaign for this particular advertiser. We need to have an autopilot. We need to have something that can operate without a human in the loop all the time. So that's why we need something better than just the classical linear program type solution. And that's why I will introduce the solution that we have in place now, and that permit this decoupled implementation. And to understand how that solution is, very intuitive, I will make use of this chart here. So what you have here is something where if we represent one advertiser, and suppose that we're interested to deliver ads to people in, say, California. We're interested in deliver maybe people between the age of 20 and 50 in California. Because all of users that meet that criteria, they are part of the targeted audience. And each such user is represented by a black dot in this chart. or actually each interaction that user is making with a web page. So each black dot here is one opportunity to show an ad. And the two properties of that impression that we care about is the fact that there is a certain event rate. So it's a certain there's a certain probability that Mihailo will convert if if we are showing an ad to him. So that is represented. So if one dot is Mihailo, another dot is me, a third dot is Kathy, etc. So there are different users, there are different event rate probabilities, are different with different likelihood to actually buy a product if we're showing an ad. So that is represented by the vertical axis. The horizontal axis is the highest competing bid. That is what some other advertiser would be willing to bid. So we then if we have all of those black dots that we're targeting, then the question which of those users are the ones that we should care the most about to show ads to? Well, that it's pretty obvious that the users want to show ads to are the ones with a high event rate and also a very low highest competing bid. So now I'm considering only the second price cost model. So we want to show ads to people in the top left corner, and ideally not unless we have to people in the bottom right corner. So that we get an idea about what users are the ones that are highest performing. Another way to really kind of appreciate this is to look at two different impression opportunities that are going through a straight line through the origin. So those impressions, they have the same ratio of event rate and highest competing bid. So one has an event rate of 0.8 and the other one 0.4, but the one with a 0.8 event rate would cost twice as much. But any impressions along the straight line going through the origin, they are equally appealing to me as a bidder. So that sort of helps us to then appreciate that what we want to, the impression we would like to buy are the ones in the top left corner. And only to the extent necessary do we want to show ads to people down in the bottom right. So what it really comes down to is that we want to bid, if we're bidding along the straight lines, if we're bidding proportionally to the event rate, and if I'm just adjusting the angle of that line, that means that for all the impressions in the green shaded region, our bid will be higher than the highest competing bid, and we will win them, while the ones in the bottom right, we will not win. And then we're just adjusting the angle, which we call U, so that we are spending the right amount in terms of budget, so the right number of dollars per day, and also so that we're not violating the constraint that is imposed on the effective cost per conversion. So in this context, that we're having actually a clear control problem, which is to adjust U. And the second part of the problem is how do we are estimating event rate. We don't need to estimate the highest competing bid, because that will work out itself during the auction. So, but we need in order to submit the bid, we need to know U and we need to know PI. So U is a campaign property, so that doesn't need to care about the individual user, while the event rate PI is for each individual impression. So then what we have obtained here is an architecture that consists of two components. So optimization engine that was formulated just as a constrained optimization problem previously can be broken down into one component, which is the so-called event rate estimation problem or component, which makes use of as much data as possible and that you can make use of to do a better prediction of the likelihood that someone will convert. And so that depends on whatever data the user has allowed to share, but it's historical data, it's big data, and we're using accordingly algorithms that can process big data. The control component, on the other hand, is consuming the constraints, which are simply the budget constraint and the effective cost per conversion constraint, and are consuming feedback, which is only campaign level feedback. So how much did I spend over the last, say, 5 minutes? And how many conversions did I observe over the last 5 minutes? So based on those two feedback signals, which are campaign level and not based on individual users, we can estimate what is the spend rate and whether or not we are violating the budget constraint, or if we are violating the effective cost conversion constraint. So control can then adjust you without needing to care explicitly about what this PI is. And then the product of U and PI will be the bid that is submitted to the market and to the auction. And then this system can then run 24/7 to manage the campaign of the advertiser. So now I will sort of just kind of reflect on what this means, that now that we have decomposed the problem to solve it in this way, and to appreciate kind of what speed that we can achieve with this. Compare this with, for example, human eye. So when you blink your eye, it takes about 0.3 of a second. So that's pretty fast. You can barely see that at all. So that's very fast. A hummingbird, during those 0.3 of a second, can flip the wings about 20 times. And if you've seen a hummingbird, I mean, you're probably impressed about the extraordinary speed in how they're flapping their wings. But then during that same time, that this DSP system that I just presented on a high level can evaluate and submit bids on 300,000 impression opportunities. So that's the speed that it's doing. That's the speed it has to do. But it also helps you hopefully to appreciate that the scalability of solution and the design choices made in the algorithms is extraordinarily important. So with this said, I mean, I will discuss the different components. I will first say something about the event rate estimation component, and then something about the control component, and then some additional work after that. So, all right, so event rate estimation. So the event rate estimation then, as stated earlier, has the job of computing an estimate, the best possible estimate of the likelihood that someone will convert if shown an ad. So if I show an ad to Mihailo, what is the probability that he will like the ad so much that he clicks on the ad and buys the product? Or if I show the same ad to Kathy or to Scott, etc. And without going into the finest detail, this slide demonstrates sort of the general approach to this, and what we're doing is that we are having a team, first of all, scientists with a wide range of backgrounds that are working on data to do a lot of modeling and system identification offline, and are doing training based on the really heavy computational artillery involving XGBoost or deep learning, and that will help them to come up with sort of some preliminary understanding about what matters. I mean, what are the features of a user that dictate the likelihood for them to convert. Now, we can't implement a deep learning network that can run in just a millisecond. So we are leveraging on the insights that we have from those complex models to implement the sort of simpler models, which could be logistic regression-based models or field-weighted factorization machine models that are then more lightweight, and that can be trained still offline, but then can run and use various lookup tables and scoring in real time much faster. So we're training those models outside of that very tight feedback loop, but then they're running to compute or to evaluate the actual conversion rate probability online. So that's sort of the event rate estimation, and some of the features in making use of it could be ad field features, so information about the ad itself. If it's a visual ad, it could be any information we have about the ad creative or the type of product, if we're trying to sell a magazine subscription or a car or perfume or whatever it is. So that's what goes into the ad fields. Context features or context fields, that involves things elsewhere on the web page in question. It could be, what was the article that Mihailo wanted to read, and besides which we're showing the ad. Because the more we know about that information, the better we can possibly choose which ad and how valuable it is to show a particular ad to Mihailo. And other things is whatever we know of Mihailo explicitly. I mean, do we know his age? Do we know that he's a male? Do we know that he's a professor at USC? And if he hasn't blocked cookies, I mean, do we know anything about his past internet behavior? What web pages he has been to before? Did he maybe go to some web page to look out some product he was considering to buy but didn't buy? That information obviously can be extremely valuable, because if we know that he was actually considering to buy a pair of new soccer shoes, but he didn't buy them, then that information can then be leveraged, because then maybe we should show him soccer shoes this time around. It could be publisher fields, things that are not just specifically about the article that he's reading now, but about the publisher overall. So all of those fields and those type of features are used by the event rate estimation system. But then some of the challenge is that the likelihood for people to convert, I mean, it's typically very, very small. I mean, it's ranged between 1 in a million to 1 in 1,000. So it's very common that only 1 per 1,000 or per 10,000 impressions that are shown will actually lead to a conversion. So that translates into very delicate challenges in the statistical estimation problem. And the number of internet users is extraordinary. And we're talking about 1+ billion internet users, and we're talking about more than 1 million raw features that needs then to be pruned down to identify what are the features that matter. Also, there's typically a significant impression to conversion latency, because the fact that we show a pair of soccer shoes to Mihailo today doesn't necessarily mean that he places the order today. Maybe he will think about it, and maybe not until on Saturday, when he has time to think about what he needs for the next game. That's when he will return to the web page and actually buy the soccer shoes. So then we have this 4-day latency that matter. Then there is a certain scoring time service level agreement, by which I mean that we need to submit the bid for a possible impression opportunity within just a few milliseconds. So all of those are kind of then just translating to challenges. So that's what I'm going to say about the event rate estimation. So that's the first component. The second component is the control. So I will, as an analogy, I will compare this with a cruise control of a car. I mean, when you have a cruise controller of the car, you set it, you want to drive 65 miles per hour. And then regardless of if you're going uphill or downhill, the cruise controller will detect that and will adjust the throttle into the engine and will inject more or less gasoline so that the car will stick to 65 miles per hour regardless of those external disturbances. To a large extent, that's the same thing with a control system for online advertising, that we're having constraints. We have a budget constraint and we have an ECPA constraint. And if you remember this, the figure I showed earlier, where the control problem is really to adjust the angle of that straight line U. So, and then what that has to deal with is a dynamic competitive landscape, that if the competing bids are going up, that means that we're going to win fewer impressions and we're going to then pace behind in terms of the budget delivery. And then in order to keep up and spend the budget in fall, we have to increase the bids. And the control system is doing that by adjusting the value of U. And that's virtually the same thing as what the cruise controller is doing. So you can think about ad learn control as the ad space equivalence of an ad space cruise controller or an autopilot. And so some of the things that are achieved with this is that, well, if it's well designed, we can achieve sort of stability by way of sort of state-of-the-art nonlinear adaptive control. We can achieve the maximum return of investment for the advertiser and really focus on the metrics that matter to the advertiser. It is also versatile, although in this presentation I only mentioned 2 constraints, but the way it's implemented and what it can achieve is much more. That we just have to formulate the right problem, we have to decompose it into the right subcomponent, and then we just leverage on feedback control. And the way it's implemented is forward-looking, so that it will support the next generation business needs as well. And you have some time series plots to just give an example, and this is over the course of a couple of weeks, and the a little bit thicker, darker red vertical line indicates when we were upgrading the control system to something, to a system that was doing a better job. We can see that all of this, the daily revenue, the daily spend, in the first subplot stays the same. So every day we are spending about the same number of dollars per day. But when we upgraded the control system, we were able to reduce the effective cost per conversion significantly. And you can also see that in the third subplot that the daily as well as the hourly number of conversions went up. And all of this was achieved by having the adequate algorithm is computing U, so that straight line going through the origin in the rightmost plot. So that's a control system. So that's the second component. So what I presented so far is the decoupled solution to solve the problem of optimal bidding for second price inventory. So I mentioned before I went into the problem statement that impression can be sold either on first or on second price cost models. And it's easier to present the solution for the second price cost model because we don't need to explicitly care about what the highest competing bid is, because that sort of will be figured out, I mean, that the controller will adjust U accordingly. But the question is, what is the modification that is needed if we are going from a second price to first price cost model? So here, kind of to recap the approach for the second price cost model, we have here the block diagram consisting of those 2 components, event rate estimation and control, that the product of the outputs of those subcomponents define the bid, and that bid is submitted to market. And then the visual representation at the bottom shows that in this green shaded area, that's the awarded number of impressions, and we are just adjusting U, and the optimal bid is then the product. Now, if we're going to the first price cost model, then what we end up, although I don't have time to explain it in great detail, but what it ends up being is that we just have to add one more component, which is a bid shading component, which means that we're not actually then bidding along that straight line anymore, but we are bidding somewhere between that straight line and 0. So that's why here, if you look in the green shaded region, is that now it's not called awarded impressions, but candidate impressions. Because then if our bid or the product of U and PI, suppose, is $2. If we happen to know that the highest competing bid price is $1, in a second price cost model, it doesn't matter, then we submit $2. But in a first price cost model, we wouldn't want to submit $2 if we know that the highest competing bid price is $1. Instead, we would rather submit just $1.01. So we would rather than reduce our bid from 2 to slightly above $1. Now, in practice, we don't know beforehand what someone else is willing to bid. So that's censored information. But if we have an ability based on historical data to make an estimation of what the highest competing bid price is, then we can strike the balance so that we can reduce the bid to somewhere below $2. So if we know with almost certainty that the highest competing bid price is between 90 cents and $1.10, then we would reduce our bid from $2 to $1.10 or a little bit below that, because we do want to win this impression, but we don't want to pay too much. So that is what then the bid shading optimization problem ends up being. It's a component that uses AI to compute the optimal shading factor, kind of with objective to compute the bid BI that is the product of 3 different components. It's a shading factor, UI tilde, it's a campaign level control signal U, and it's an event rate prediction PI. That's sort of expected, what we call expected surplus per bid. And what expected surplus per bid really is it's trying to strike the optimal balance between reduction of cost and reduction of win rate, because we want to win the impression, but at the lowest possible cost. So that's what you see here in this chart. Is in the left is the shading factor that is adjusted over time, and you see for a large portion of this time series it's around 0.8, and you can see in the middle graph how much that shading factor impacted the win rate. So we ended up winning slightly fewer impressions, but we ended up paying less for those impressions that were awarded. So that pretty much wraps up. I mean, it's the third component that is completing the solution for optimization of online advertising, and then obviously under the hood of those 3 components it goes a lot of algorithms, a lot of mathematics, and it's work in progress, and so a lot of people working on it. And it's not only people at Verizon Media, but the problems that you have been presented here are the same type of problems that companies like Google and Facebook and Amazon, etc., are working on and trying to then make better as time goes on. And so hopefully what I've been able to convey in this presentation is that online advertising does involve a lot of challenging systems engineering problem, and it may decompose into sub-problems involving estimation, control, and what I here call sub-optimization. And your background in electrical and computer engineering, I mean, those are excellent backgrounds to work on problems in programmatic online advertising. And you may already know people working on it, and there's a lot of publications out there, and timing wise is happen to be good at this week. If any one of you is a member of the Control Systems Society, then within the next few days you will receive the next issue of the Control Systems magazine. And I've been very grateful and fortunate to have a feature article in that issue coming out then in a few days. So that's one avenue where you can learn more. So although in this feature article I will primarily talk about the control problem that I touched upon in this presentation, but that's sort of one place where you can learn more. And by that, I thank you for the attention, and I would be happy to answer questions.
Thank you, Niklas, for wonderful presentation. So we'll actually share your article from Control Systems magazine with our students, so that everybody has an access to it. So what I would recommend now, I'll open the floor for questions, but please either write your questions through chat, and then I'll read them to Niklas, so you can just chime in immediately and ask Niklas question directly. Either way works, but just one at a time, please. So the floor is open for questions.
And you feel welcome to ask any type of question. It doesn't need to be around this presentation, because I know that this series of talks is to give you a sort of flavor about what it is like in industry. And I mean, if you have questions about my experience, the transition from academia to industry, or yeah, ask me anything that you may pondering about.
Yeah. So please use this opportunity.
Maybe so. To start off, I can bring up something that many people often ask me when they're in grad school, and that I was concerned about myself, and before I decided that I wanted to go out in industry, was that, well, am I going to work on interesting stuff, or am I? Is it because I mean, as a PhD student, I mean, you typically work kind of on the sort of leading edge research, and you challenge yourself, and you may have this fear that you go out in industry, and then you're just going to have an opportunity to apply sort of things that other people have developed in the literature, and it's going to turn into that's a tedious and not very stimulating experience. And I can't talk for the experience of everybody else, obviously, but I mean, as far as my own experience is that I've ever since I graduated, I've had the pleasure to work on really challenging problems that has not allowed me to just plug in what I find in textbook solutions. I mean, that applies to both when I worked with evolution robotics, because there I was presented a problem to how to do simultaneous localization and mapping for mobile robot, and that in itself is a challenging problem. And when I switched to online advertising, kind of then, well, how do we solve a problem? The control problem here, for example, it's non-linear, time varying, stochastic, etc. So it's a lot of challenges.
See, maybe I can follow up on that before our students ask questions. So obviously, you very nicely demonstrated that you're bringing together a variety of tools to solve a problem at scale, of extremely large scale, in real time, very quickly, and in addition to tools from optimization and feedback control, obviously you guys are bringing lots of tools from artificial intelligence, machine learning. You're learning about your users and so on. So can you talk a little bit perhaps about this confluence of different ideas and about composition of your team at Verizon Media? So what kind of backgrounds you have there, and what kind of team members are you looking for in your effort to expand, and not only at Verizon Media, but generally speaking in online advertising industry? If you can just comment on that a little bit.
Sure. Yeah. First of all, there is no education program for an online advertising scientist. So it will be interesting to see in the future. Maybe there will be, but the ideal individual, I would say, that would work on problems like this should have an expertise in multiple areas, and then say computer science, control engineering, statistics, and optimization, kind of that sort of blend of backgrounds. I mean, it's hard to come about people that have an expertise in all of those areas. So we're having a mix of people, and I would say very often when we hire people, in particular fresh from grad school with expertise in one of those areas, I mean, they typically lack in some other areas. So it's what we look for is someone that is not only bringing a solid foundation of something, but more importantly is bringing the ability to pick things up. So if it's someone with just say background in engineering, say control engineering, then it's very often a control engineer may think about the world as Gaussian and may not really have kind of this mature appreciation of random variables beyond sort of a normal distribution. So then it's important that the person we hire will sort of have the ability and interest to broaden the horizon. Moreover, I mean, if you are having a background in statistics or control engineering, you may be somewhat weak in the computer science aspect of things. So then they have to be the ability to pick that up. And then on the flip side, people which has an expertise in computer science, they very often they may be very savvy to use sort of black box implementations of algorithm, but they may not have quite the same sort of appreciation kind of for the underlying sort of mechanism, dynamics, and that goes into those algorithms. So although we would appreciate someone that has an expertise in all of those, that's not, an option. So we're hiring people from all of those different areas. So Besides what I mentioned, sort of computer science, statistics, feedback control, optimization, action theory, operations research, physics. I mean, it's a wide range of it, and working together and learning from each other and complementing each other and taking different approaches to solving the problem. And then we are doing extensive A/B testing of whatever candidate solutions we're developing, just to see what works and what doesn't work.
Sure. So if I can follow up on that just a little bit. So obviously, industry is, at least for outsiders, the perception is that, you know, computer scientists are running the show here. And at the same time, you brought a background that was perhaps different from people who were heavily involved in this type of problems back in the day when you joined advertising.com, and you certainly pioneered the use of techniques that are traditionally rooted in electrical engineering in this emerging area. So just for an outsider to an area, can you just expand a little bit how this shifted paradigm relative to what computer scientists at the day were doing, and what new opportunities, feedback perspective that is common to electrical engineers brought to the table?
Well, I mean, I would say up until 2005, or even fewer players. I mean, in the show playing, and then there was a before user level data was available. So all the data was available was pretty coarse, and so at our company, most people then that were developing algorithms, they had a background in operational research. And I can give a little bit kind of a side story that the company that was founded in 98, TechCrunch, they partnered up with a consulting company in Mountain View called Onward. And Onward was founded by three members, three people. One of them, his name was Rob Leuenberger, and you may recognize the name Leuenberger. So his dad is the famous David Leuenberger from Stanford. And so David Leuenberger was actually then an advisor of that company, and when they developed the first generations of optimization system. And it's a little bit because of that name that I decided to go into this company. But so in the beginning, it was this operations research approach. And then within our company, we developed kind of that one aspect of the problem is the feedback control aspect. And I think that's here to stay. Because there are certain parts of the problem that can be solved using, say, deep learning, etc. But there are some parts that are not easily replaced just because we don't have enough training data, etc. So I think that now compared to a few years ago, there are probably more computer scientists involved, but not there are not more computer scientists working on the control problem, for example. But just the fact that there is much more data just in general available that can be worked on, so shifted through for insights and for the event rate prediction. There's some aspects of the problem that lend themselves very well for kind of that big data machine learning. So right now, overall in the research org, it's dominated by computer scientist backgrounds. So it's more computer scientists, but there are certain areas of the research problems that they do not have the background to work on. That requires a very, special, different role. And it's not only control, which is kind of what is closer to my heart, but also some statistics problems that most computer scientists don't have the background to work on. So it really takes a combined effort.
Yeah, very good. So unless somebody chimes in, I'd like to thank Niklas for his wonderful presentation, for giving us a generous overview of the industry and of his approach to the problem. For me personally, this was educational experience, and I hope that our students would benefit from this, not only in terms of immediate learning opportunity, but perhaps in terms of putting online advertising on the list of potential careers where they can see themselves maybe in the future. Thanks again, Niklas, and hopefully we'll see each other sooner rather than later.
Mihailo, can we actually just ask the student to unmute themselves and just give Mr. Karlsson a round of applause?
Oh, that would be great. Thank you, Kathy. Of course.
Yeah, so if the student can just unmute yourself, and then we'll just give Mr. Karlsson a round of applause.
Please, everybody, go ahead and unmute yourself. We need to do this in a coordinated fashion. And then Kathy is going to lead the process of doing this.
Yeah. So thank you, Mr. Karlsson. Yeah.
Yeah. Thank you, Niklas.
Thank you, Niklas.
Thank you so much for the opportunity.
Thanks. What a great presentation.